to the last lecture of Mitchell Luskin. And I guess you don't have a title there, but I'll let you go anyway. Yeah.
Okay, thank you. So what I want to do first, and this will probably take maybe half an hour, half of my slot, is to kind of review and then finish this kind of formulation of how to do relaxation for tri-layer and multi-layer problems, and so giving a very general kind of picture of this. Okay, so then, after I do that, there's a couple of options. I'll have to see what the time is. I basically have maybe three, as part of preparing, I ended up with like 3 more lectures, I think. So what I may do is just go back to density of states and kind of try to clarify some things there, and then, anyway, let's just see how it goes. Okay, so let me kind of start, kind of review this description we had. So this is just a visualization of a tri-layer, essentially a tri-layer change, you might say, but it's a visualization for the tri-layer 2D materials okay, so here, so what we have is we kind of view ourselves as describing a viewpoint. So omega, right, which is in little omega, in cap omega, describes a viewpoint. So you're standing here, okay, and and from that viewpoint, I see all these atoms. I see these three lattices, like 1, 2, and 3, and I can describe the lattice, each of the lattice by a shift vector, gamma 1, gamma 2, and gamma 3. Okay, so that describes the viewpoint at that point. Now, okay, so what I'm going to do is I want to formulate a model for the relaxation, and that what is that? And what that model is going to is going to be based on the displacement of the atoms, and the atoms are these circles. Okay, so but I'm going to have to. But what I want to do is I want to formulate, like use a Cauchy-Born and things like that, and to do that, I'm really going to have to be able to define displacements at, say, these points where there's no atom. Okay, so there's no atom there, but I only have a displacement at the atomistic position. Okay, so I'm just telling you where this is what we're going to end up doing. Okay, so this is just our generalization of incommensurability for a p-layer system. You sum k reciprocal lattice vectors, one from each layer, they equal to 0, and the only way for that to be the case is if each of those reciprocal lattice vectors is 0. Again, that's the same as the other definition I had, that you stand on any point if you actually stand on any point here that you'll see a unique viewpoint from the point of view of a unique configuration from the point of view of the reciprocal lattice space. Okay, now I can view myself as, I can say, okay, this is my viewpoint. Like I said, I see all these atoms, and then I can ask myself, as I translate, say, by A, forward or backward, how does the description of the viewpoint change? Well, it changes because each of these gamma 1, gamma 2 change, right? Because if I move forward a little bit, okay, then gamma 1 gets smaller, like gamma 2, right? What is gamma 2? Gamma 2 gets, more negative. Gamma 1 gets less positive, okay? So how does the viewpoint change as I move through the tri-layer? Well, okay, we can view these translations, okay, as some kind of group T sub A, and so actually when you move forward by A, actually it should be gamma 1 minus A, gamma P minus A. Okay, so or you might want to call this okay, T of minus A. But anyway, that you can work that out. But anyway, so the ergodicity result is exactly this. It's exactly the same thing as what we had for the bilayer system. Okay, so this is this is kind of similar to if you were talking about any kind of dynamical system, right? You can say, okay, you can sort of sample the dynamical system by your dynamics moving around, and take the average, take the probability of being in any particular point, just following the dynamics, right, of your whatever it could be, an ODE or whatever it is, or you could actually say, okay, if I'm only interested in the kind of probability of being in any one position, then that's the same thing as just evaluating an invariant measure, right? Say Boltzmann distribution or something like that. So this is just a generalization of this notion of ergodicity that comes up everywhere in dynamical systems. Okay. Now, so within this big set omega, within this big set omega, that described all viewpoints, right? It described a viewpoint where you're not on any particular atom, but if your viewpoint was the viewpoint of an atom, okay, then one of these gamma 1, gamma 2, or gamma 3 has to be 0, okay? So if gamma 1, gamma 2, or gamma 3 is 0, then your viewpoint is the viewpoint of an atom, okay? So we describe that set by this by X, by capital X, okay? And in kind of fancy dynamical systems language, this is called the transversal of the whole, okay? So it just means gamma J is 0 for one of the layers, okay? And we want to represent our atomistic deformations, right, as a map from X to R2, okay, and so U gives the displacement, right, of each layer. But now let's just focus on the displacement of layer J, right, and the displacement of the atoms in layer J. Okay, if I say, okay, if I'm actually sitting at an atom in layer J, then what do I get to do? I want to know what the displacement is when I shift all the other layers. And so that says that if J was 2, then I can actually then gamma 1 and gamma 3 can take different values that describe the relative positions of the layer 1 and 3 with respect to that atom in layer 2. Okay, so I'm describing all kind of all the environments that I might see as they move through the body. Okay, and this is this just says this is just a description of how you go back and forth from a description of a displacement in configuration space and real space. Okay, so how does that work? Okay, let's say you're starting there. You can let omega be 0, right? Then this says let omega be 0. Okay, you're sitting at some omega being 0. Okay, you're sitting there, and omega 0 is the case where all the atoms are. Okay, if I take this omega 0, right? That's the case where all the atoms are going to line. Your viewpoint is so that there's you're sitting there with an atom, all the atoms in layer 1, 2, and 3. They're all there's an atom at the origin for each of those layers. Okay, I can start anywhere I want. If I start there, then this says, as I now translate by Xi, right, where Xi is an atom in, let's say, a layer J, okay, then this describes how the environment right, around that layer changes, right? So if I, because these are incommensurate layers, as I move from atom to atom, the environment changes. Okay, so this just describes, so this just describes moving to a new atom C, how the environment is changing, and that's just the displacement in that new state. Okay, so all right. I mean, I know this takes a little time to get comfortable with, but I think once you get comfortable with it, it's quite intuitive, as anything, of course. Okay, so now what I wanted to do is I want to say that okay, and this is the kind of that you might say. Okay, let's just say that somebody gave you an empirical atomistic potential. Leonard Jones, embedded atom. There are all these potentials, okay? And so what do those potentials say? They say that if you're at a body, it gives you the energy the energy associated with that particular site, okay, and that energy depends on the relative configurations of the atoms around me. Right, as I said again, same as Leonard Jones molecular dynamics, same as gravity, electrostatics, etc. So we can describe the energy at in each configuration based on the environment, which is described by omega. Okay, and then that's depending on both so this describes the in-plane, the positions of the in-plane in the environment, the atoms in the in-plane, right? This, you see, is like a two-body, it's like a many-body potential. So we have the pairs, the relative displacements in plane and out of plane. So this is just a very general form for a many-body empirical potential of an atom, okay? And now, what this is saying is, so I know so what is it I'm trying to get at? So let's say so given displacements of all these atoms, okay, now I want to compute the energy, the average energy per unit area of this body, and to do that, I have to take a large body limit. I have to let R go to infinity, compute the energy of that finite system, normalize, right, and then ask, as R goes to infinity, does this thing converge, and what does it converge to? Okay, and that's exactly what that ergodicity theorem tells us what to do. Okay, so the ergodicity theorem tells us that we can exchange this exchange this sampling, you might say, over all the atomistic energies in some radius of r. We can exchange that from simply going layer by layer, right, and then taking let's say an atom in each layer, J, and then looking at all the relative kind of disregistries of the other p-1 layers, okay, and ask what is the energy of each of those and average that, okay. So again, I'm going over a large limit in space, and I'm comparing that to just evaluating with respect to some invariant density, okay. So and like I said, if you've ever studied statistical mechanics, this is exactly what's done there. Okay, so here, so this is a very, very compact formula. Okay, but already, and it's not a formula that we are really going to want to implement. Okay, that's the thing. We have to do more work to get a model that we can actually put on the computer and study, let's say tri-layer relaxation. Okay, now let me notice already what we see is, right, each individual, say each layer J, right, its environment is a 2p minus 1, a 2 times p minus 1 dimensional torus. So each of these xj's, right? So the gamma i's are the unit cell of layer I. Okay. So the environment that an atom in let's say layer J, its environment, we get to shift all the other p minus 1 layers around in this unit cell. Okay. And each each layer has a 2-dimensional kind of space of dysregistries, and we have p minus 1 of those. So this integral is a 2 times p minus 1 dimensional space. So for a tri-layer, you really have to solve a 4-dimensional problem in space, right? So remember, p equals 2. P minus 1 is then 1. Okay, then we have our 2-dimensional problem to solve. That's what we saw in the first part. We did a bilayer. But if you want to solve a tri-layer, right, you got to solve a 4-dimensional problem. You want to solve a 4-layer problem, you got to solve a 6-dimensional problem. So if you really want to do it right, that's what you got to do. Okay, and we've done that in the case of tri-layer, and I'll show you some results at the end. Okay. Okay, so let's kind of work a little more on this and turn this into something that we can kind of again analyze, do PDE, do numerical analysis on. We have to do more work. And first of all, okay, so let's just go on here. Okay, so the first step is to kind of separate the intralayer interactions and the interlayer interaction. So the important thing about these problems is that the intralayer interactions are much, much stronger than the interlayer, right? Because the interlayer interactions are very weak. They're van der Waals interactions. That's why the layers can easily slide, right? But they're hard to stretch. Okay, they're rather stiff, but they're easy to slide. That's again because lots of these 2D materials like graphene come from lubricants. Graphite. That's why it's a lubricant. The layers slide easily on one another. Okay, so this is a much smaller. So this term accounts for much smaller forces, yet it does have a big impact. We'll see. Okay, so in the end, if you look at our paper or something like that, you can, we actually characterize, so we kind of, we do a lot of inverse function theorems and things like that, and implicit function theorems, and somewhere along the line, right, we have to show that we have to invoke that this is small relative to that. So we do that. Okay, so. So let's first look at here at the intralayer modeling. Okay, so again, I no longer have that very general many-body interaction, right? The general many-body interaction says an atom, right, is really depending on atoms in all the layers. Okay, but I'm just saying that we can separate it out into the strong interactions have to do with just interactions in your plane. So this is now, so if I just look at this problem, this simply is a classical 2-dimensional crystal problem, okay? It's all set up for, Cauchy-Born and, everything that kind of people here, or a lot of you have worked on. So the intralayer is, okay, so we'll, so remember though, that we have to study this for each configuration. So for J, remember we're layer J, and I want to study the energy associated with the atom, right, when in configuration omega, right, and gamma J, and omega, and the jth component of this is going to be 0 because my viewpoint is at an atom. My viewpoint is going to be at an atom. Okay, so then by ergodicity, we come down to this, okay? So now again, this is not, right, so this is something not easily implemented because, right, this corresponds to a difference, not a differential operator. We're eventually going to want to have a differential operator, right? Remember, DJ corresponded to all the differences between an atom in layer J and all the other atoms, right, in layer J. So it's just a bunch of differences. Okay, it's looking at all the relative distances. Okay. Now the environment is still filled, right? The omega says the environment is still fit. You know, so if you have the interaction of a layer, different layers in layers J, it also is affected by the atoms in the other layers. So that's okay. So we'll come to, and that's why we integrate over all the environments. Okay, so as I said, you know, we have to somehow, to get a real continuum model, we have to do some interpolation. So we have to be able to define all these things, like this registry, you know, for sites that are not on the atoms, okay, that are in between. So I think we, as I mentioned, the disregistry. If I go back here, right. If I move my viewpoint through this system, the disregistry, right, like gamma 1 is going to be oscillating, right? Gamma 1 is going to be oscillating, right, on the scale of the atom, okay? On the other hand, if I look at if I just, let's say if I go from atom to atom on layer 1, right, and I look at the disregistries gamma 2 to gamma 2 and gamma 3, if I go from this point to that point, you know, gamma 2 and gamma 3 for this point and that point change very little if the relative lattice spacing is small, okay? So the disregistry is actually a smooth function at the lattice points themselves. Okay, so what is it like? It's like, okay, if you just take a, some harmonic function with a period, right? And if you sample it on a period slightly smaller or larger, right, then the value doesn't change much, okay? If you do that, okay? So that's all we're doing here. We're sampling an oscillatory a periodic function. We're sampling a periodic function at points that have a period slightly off. Okay, so that's what we're doing here. So the disregistry is actually smooth evaluated at the atomistic points. So that means if we want to have a smooth disregistry, then we have to do some interpolation. Okay, so here this just shows you. Okay, so let's just say that. Okay, so let's say we're in some configuration, little omega. Okay, and I want to know the local disregistry of layer J with respect to layer I. Okay, so I want to know that disregistry at this point here. Now, okay, so these are the atoms at the atoms for layer J, and these are the atoms from the lattice of layer I. Now they're slightly different. And so each of these, so we know what it means. We know what the disregistry is for the disregistry of the atom of one lattice with respect to the other lattice, right? That's just right. It's just this vector here. It's just these vectors. We know what that is. That's well defined. Okay. What we don't know is what to do in this point. Okay. So what we do is simply bilinear interpolation of the disregistry, at these other points, because these are really close. Okay. We do a bilinear interpolation, and if you do that, you come up with a very simple formula. Okay. So this formula, this is a formula, right, that now gives me local dysregistry, right, for any gamma 1 through gamma p, right, I'm no longer, what am I saying? If gamma j was 0, right, then that's where it's well defined. Okay, when gamma j is 0, that's where it's well defined. Gamma j is 0 meaning says, okay, you're sitting at one of these atoms. But if I'm not, then how do I define the dysregistry? Well, what you do is it tells you you subtract out gamma 1 times gamma j inverse times gamma j. Okay, that's what you do. Okay, very nice formula in the end of the day. Okay. Okay. So and again, if you're just doing, if you just had some twist, if you had just some twisted system, then these are just some rotations. Okay. So we can define dysregistry everywhere in the body. Okay, that's real nice, right? I can really define what it means for, in a continuum sense, what the dysregistry is locally anywhere in my body. Okay, so now, like I said, the model. Okay, so the model in the end, what we're gonna do is we're gonna solve for the displacement at the atoms. Okay, so the displacement at the atoms is defined by restricting the displacement to the case for uj where gamma j is equal to 0. Okay, so we'd like to be able to define a displacement, for any point in space. Okay, and again we do that by interpolation. You could actually go and just interpolate the displacement at these points and okay, and now that's up to second order. It's the same as essentially doing a interpolation of the of omega. Okay, so pi j. So that interpolation is just given by this. So interpolate. So let's say you're in the situation where so omega. So gamma j is not 0. Right, now we take pi j omega, and we end up with something where the jth entry is 0, okay, and then we have the relative shifts for the other omegas. Okay, so in other words, what is if I want to evaluate u sub j here, then I essentially what I do is I create a continuum model by essentially, kind of interpolating and getting some kind of relative display. I interpolate where I get all these the relative shifts of the other layers. Okay, so we have a formula to extend by interpolation the displacements that are defined at lattice points into all of space. Okay, now comes the big. Okay, now if I want to end up with differential equations. We haven't gotten any differential equations yet. Okay, so how do we get a differential equation out of this? Well, what we want to do is let's take the spatial gradient, okay, of our interpolated displacement. Okay, so to do that, right, we have to then apply the chain rule, right? Because we have to differentiate u sub j, right, with respect to configuration variables. And then I have to differentiate this interpolant. Okay, and if I carry that out, then I get this very nice formula. Okay, so I can describe the so that means what I want to do then is what I can do is then go ahead and define this kind of spatial gradient, of a function really defined in that space x, right? It's a spatial gradient that is defined on the space x, right? Meaning just knowing the displacements, for atomistic positions, and it's given by this formula. Okay, so let's look at this formula. So this here says this is just so essentially what we do is for each I not equal to j, for each of the, say if j was 2, we look at layer 1 and 3, then we take this is just a normal gradient, right, with respect to configuration variables of uj, okay, multiplied by ai aj inverse minus I. Okay, now, this theory is really working well when ai aj inverse minus I is small, actually, right? So in case if just a bunch of angles that are shifting, right? This is really of size. This is of order theta, right? If you have rotations of size theta, this is of order theta. Okay, so what that means is that okay, so you're kind of multiplying, gradients in configuration space by things of order theta to get something smoother over here in with smaller gradients in space. Okay, so now here. Okay, so let's go back to our intralayer energy. So before I had these differences. Now I'm going to replace that by these gradients. Okay, so this really is a differential operator, right? In what? What is it? This is a differential operator in the variables gamma I not equal to j. Okay, so again, if we're looking at a tri-layer problem, p is equal to 3. This is a differential operator in It's a differential operator in 4-dimensional space. Okay, so this is a differential operator in 4-dimensional space, right? And of course, this is our 4-dimensional. This is a 4-dimensional tori. So this is now our this is now a genuine nonlinear elasticity model, you might say, for the intralayer interactions. Okay, now so something now from here you can go further and actually make a Cauchy-Born assumption, things like that. You can get a true Cauchy-Born model, okay? Or you can just for what we've done for simplicity is just use linear elasticity or just any other nonlinear model. Okay. Now this is kind of what's interesting too about this is actually the PDE is actually a non-elliptic for p greater than 2, right? That's because if you look at this, right, you're looking at that this differential operator. So you're in, let's say, for p equal to 3, right? What you've got is it's sort of like you've got like 2-dimensional Laplacians, okay, but you don't have a 4-dimensional Laplacian. Okay, that's because each of your differential operators is coupling in plane, right, to a 2-dimensional set of atoms. Okay, so nonetheless, this is okay. So we've actually been able to show this actually is what's the word? Anyway, it does have solutions, etc. But it's a difficult problem, and and again, we've been able to actually go and numerically solve this. Whoops! Uh-oh, what the hell's going on? I wonder if I've lost power. No? Okay. Okay, good. So we have an interesting PDE problem here. Okay, so now what about the interlayer misfit energy? So the interlayer misfit energy, right? So now what do we have to do is is actually we have to define some kind of interpolated local disregistry. So just as I did in that two-dimensional case, I need to define my local disregistry. If there were no displacements, then the disregistry would just be, and we're only looking, I'm assuming that the interlayer, only the important interlayer interactions are the layer above and layer below, okay? So if I do that, then it depends on the disregistry, right? We saw that in p equal 2, and then we have to account for like the displacement, because the displacements is changing what that actual disregistry is at your point, okay? So that's the role of displacement in the disregistry, okay? And of course, if we're just trying to define it in terms of atoms on layer J, when we go and look for the displacement, the relative displacement at a kind of a viewpoint omega, then there is no atom in layer J plus 1 or J minus 1, right? Because they're shifted. We have to do some interpolation, and so that's what this is. Okay. So finally, after all this, we get our kind of our mechanical relaxation model here. So find again UC is equal to this. Okay. Here's our PDE problem. Okay. Now let me just say that just as in the case for the bilayer system, so in the end, right, we are solving for displacements that are periodic on these environments, okay? But to actually get a real space displacement, right, we're going to be sampling on some aperiodic set. So end of the day, what's being produced, if I actually give you the picture of the displacements in real space, the atoms really are aperiodic. Okay, there's no periodicity in this problem. Okay. Okay, so let's see, oh yeah, good. Okay, let me go to this first. Okay, so yeah, so what I was doing this morning is trying to put some of our recent simulations into this, and I kind of got stuck. You know how LaTeX is at the last minute. Okay, so I was able to get the case of graphene, where you twist one layer by 1 degree and the other layers by 1 degree. So there's symmetry in this problem, right? Because from the viewpoint of layer 2, I see a twist 1 degree and minus 1 degree. Okay, so what this picture is showing me is the displacements in configuration space, right? Because that's why so it's really nice to show things in configuration space. So this is layer 1. Okay, so what we see is this gives me our displacements in configuration space. Okay, so we need to kind of map this into real space. Again, we haven't done that yet, but we will probably in the next few days. And of course, what we see is that we have the displacements are in. If you look at, because of the symmetry, right? The layer 1 and layer 3 have some symmetry, and then layer 2 is kind of, remember like we had U1 is equal to minus U2 in the bilayer case. In this case, since layer 2 is feeling both layer 1 and layer 2, the displacements are twice as strong. So okay, so this is the case of the top 2 layers are twisted by degree 1 and the bottom by degree 1, and what this picture is showing me is this is kind of the energy of the generalized stacking fault energy. It's a way of measuring the energy of the interlayer interaction. Okay, so this is the case of the unrelaxed system, right? We saw that in the, okay, and then when we go and do the relaxed system, then of course the low energy region increases. That's what relaxation wants to do, right? It wants to minimize your energy. Okay, so that's what this is. Okay, so so what we've done is, okay, so when I couldn't get into get in here, kept saying error, was we also have theta say theta 1 equal to 0.8, 0.5, 0.2, 0.1, and we keep theta 2 equal 1. Of course, and as the the relative twist theta 1 starts getting smaller, right, then small angle means actually a stronger interaction. That's when you have the large Moire cell. Okay, so in that case, you see. Okay, so I've not been able to get that in there, but we're in the process of exploring all the different configurations, etc. And again, ultimately, like I said, it's going to be then included in density of states and conductivity, and have a full-scale model for everything. Okay, so so this is just kind of a summary of this. So our configuration space formulation enables accurate and efficient relaxation in regimes with large Moire patterns, such as small angle bilayer graphene. It actually enables us to study relaxation when no empirical potential exists, such as bilayer molybdenum disulfide. Okay, what does that mean? Right? Is there actually so there are some empirical potentials that aren't that great for bilayer graphene, and I think maybe for hexagonal boron nitride, but these more complicated ones. Because remember, to construct an empirical potential that includes accurately the interlayer reaction is very difficult. Okay, because if you really want to do it, you can all do it. You can do it phenomenologically, or you can try to. A lot of people. What's popular nowadays is use DFT data and then do some data fitting. Okay, but in the end, nobody has anything decent. But as I showed you before, the generalized stacking fault energy is so much more accurate than whatever they're going to come up with in this. Okay, so and that with like a small number of parameters and invoking symmetry. Okay, so we can really nail the interlayer interactions. Okay, and now another nice thing about configuration space is that actually we get the configuration. We get the displacement as a function of configuration. Now that's exactly the input we needed for density of states and conductivity as well, right? We don't, so even if somebody did get a computation in real space, in our formulation, they still have to transform the data into configuration space, okay? So why not just solve your problem in configuration space? So you got to deal with configuration space into the day. We've been able to formulate the mechanics in configuration space. Okay, then, so we don't do, again, pretty much, I would say if you look at, there really is no other work out there that really can do aperiodic problems. Everybody else uses supercells, right? That's kind of the long-standing approach in physics and et cetera. Okay, and we're able to, here with this, we're actually able to study incommensurate multi-layer heterostructures. And in these problems, as I said, there is no periodicity in 2 dimensions, okay? If you actually look at, remember, in the bilayer system, right, we actually saw with our own eyes periodicity, right, a 2-dimensional periodicities, Moire cells. And in 3 layers, there is no periodic structure. Okay, so it enables us to overcome this challenge, and I think that's probably. Oh, okay. So let me just kind of review some of these papers again. So pretty much this lecture has pretty much been pulled out of this paper here, sitting on the archive and actually submitted to archive. Okay, so that's gives kind of the mathematical treatment. Then the kind of a little more kind of physicsy treatment is given by this. This needs to be updated. This is in PhysRev B. Okay, so this is actually out there in published form. The density of states kind of work is in SIAM MMS journal. Kind of, if you really want to understand, like in this density of states, again, in a more physicsy approach, is in this paper called Twistronics. Okay, so that actually does, it does a lot of interesting physics in that paper. So, so I really, this is, you know, I always, like for physicists, certainly I always direct them to this, and I think even, you know, I think even mathematicians wanting to get into it would find these physics-oriented papers kind of fun to read, and I mean, obviously they're not as precise as a math paper, but they actually give additional information and applications. Okay, so one of the lectures I was going to give here was sort of, okay, so so what I've done is I have described, and maybe I'm going to stop at 10, of course. If I have any time, I'll go back and, you know, after I give a lecture, then I realize all the things that are unclear, and I spend the next few hours fixing it up for the next time. So everybody's a guinea pig here. But okay, so in my density of states lecture, I realized, hey, there's some things I could have done a lot better. And again, I may just touch on that for the last few minutes. But okay, all of this is saying, okay, I'm looking at my Hamiltonian given and the variables are essentially wave function, are these basis functions centered at points. It's real space. Remember, so the entries, right, the indices, right, the indices of that Hamiltonian matrix corresponded to points in space. It was like a finite difference operator in space. Okay. Now, what we've been able to do is essentially do if you take a block transform, okay, of that full Hamiltonian, then what happens? Well, you know, if there was no interaction between the layers, you would end up with if there's no, okay, basically you would diagonalize the top layer by the block transform Fourier for that lattice. Then you diagonalize the other layer with respect to that lattice, and you have a diagonal system, okay? And that's it. That's sort of what I went through that periodic problem. So with no interaction, you can just there's just two independent layers. Now, if you turn on the interaction, there is coupling between the layers. There are these off-diagonal elements, okay? And so that's described in this paper here. What we're now working on is, of course, is a much simpler approach to this. So I had that. That would have been one of the lectures here if I. But okay, so that's next time. That's next time. So now you might say, okay, so I can formulate this, and so in the end, what do I get? I end up with a Hamiltonian instead of the entries corresponding to points in real space, to lattice points in real space. It corresponds to points in reciprocal space. Okay, so it corresponds to a Hamiltonian whose entries are indexed by points in reciprocal space. Now, you might ask yourself, okay, that's really beautiful, and it kind of you can view it in terms of some kind of scattering and things like that, which physicists like to think of. But you can say that now, but why do it? Well, the reason is that if you remember that Dirac cone, right? The Dirac cone, right? The energy. If you say I want to know all the states at a given energy, right? They really are just those states, right, at the cross section of your constant energy plane in that cone. Now, and if you had a bilayer system, then you have two cones that are close by, okay? And so what that means is you don't need to kind of include those reciprocal lattice vectors for states that don't correspond to those to the values on the cone. Okay, so that means that you can. Okay, so you have a Hamiltonian, you know, in new sets of variables, in reciprocal lattice variables. All the stuff I've done, all that local stuff and everything, all can be done in momentum space. Okay, but now I only have to use, I can actually, instead of doing all the lattice vectors, reciprocal lattice vectors within some ball of radius r, I can do a very small subset of those lattice vectors. So I can really solve a smaller matrix problem, much smaller. Okay, we don't even need to do kernel polynomial approximation and all that stuff. Okay, so within momentum space, we can actually develop a, we can develop a very efficient method. In fact, provably, we actually are able to prove a higher rate of convergence using momentum space methods. And in fact, momentum space methods are really what's turning out to be the what we're using, what we're going to be using. Okay. So anyway, so this is what else? Okay. So that's okay. So those are probably the. I mean, there's a bunch of other papers in the pipeline, but these are kind of the ones that I would most suggest. So what okay, so I think, I'm just going to take 1 or 2 minutes and go back, if you don't mind, to density of states. I just wanted to make sure people got that. Oh, so there's some point here. I don't want to belabor this, but everybody, it's fresh, it's 9 a.m. We started, so we only have to be here half the day now. Where did I do? Okay, so where did I? Maybe I didn't update this, in which case I'll just stop. I thought I created a new slide. Okay, I can't find it. Okay, here we go. I can just talk my way through that. Okay, so for those who didn't understand what this is, okay, so what I was doing here is saying, now what is this? I guess you can use a blackboard, I think, right? All right, okay, so if so what is the, the trace, so what is, whoops, there's no sum here. Okay, so what is the trace by definition? The trace says, okay, I apply a function to my matrix, and now I just look at the II entry. Okay, so I think everybody knows about this definition of the trace, right? Just means trace is just the sum of the diagonal element entries, and then this is equivalent by diagonalization, right, to the sum of G epsilon I goes from 1 to n. Okay, so this is okay. So you can see that if if you just took G, if I'm interested in the density at some energy epsilon, then I just want to take what I'd want to do is to take G to be some kind of little Gaussian or Gaussian-like function, right? That is concentrated around E, and then that would just pick off, right, all the eigenvalues in this region and give me the density. Okay, so now you might say, okay, if you say, okay, I want the real density of states. Well, okay, so this here, right, this object dH tilde, right, is simply a bounded linear function, right, on continuous functions. Okay, therefore, right, we know we can represent it by a measure. Okay, so we can represent this as, right, we can represent, what's my notation? D H tilde G, right, we can write this as, right, G of E D nu of E, so, right, so nu is my measure, that's just the Riesz representation theorem, right? And then we can go further. That's a spectral density, I would say, measure. But then you can go further. That measure, you could then write it. Yeah, I guess it's probably the Rodin-Dickinson theorem or something like that as a true density. So you can further write this as G of E, rho of E, dE. So this here, this is my density of states. Okay. So basically, I'm really what I've been doing is formulating everything really in terms of the functional, the linear functional. Now you might ask, okay, that's kind of artificial. Why do that? Well, because numerically, right? If you remember our kernel polynomial method, right? Then we have to essentially approximate, right? We have to approximate, right? When we do that Chebyshev approximation, we were approximating if you're approximating a delta function, then, right? So we went out there to p terms in that expansion in Chebyshev polynomials, and essentially the p, the number of terms you're using, really corresponds to the standard deviation of our Gaussian, right? So that means that to get a more accurate computation of the actual density means you have to have more terms p in that expansion of the delta function, okay, meaning more computational work. So bottom line, as anything else, there's a trade-off, right, between the accuracy, right, and the efficiency, okay. So again, that's all part of our analysis, but that's why, it really is, at least from our point of view, best to really focus on the density of states as a density of states linear functional, right, applying to test functions or observables, whatever you want to call them. Okay, so I think my time is up. I want to thank everybody for braving these lectures, and I'll be available for the next day and a half. So thank you very much.
We have time for